Today we want to start looking at differential equations. A differential equation is just an equation involving a function and its derivatives. An equation involving a function and its derivatives. Differential equation is an equation involving a function and its derivatives. The function is the unknown. We're trying to solve this equation for a function. The function that's the new weirdness that's going on in this. So the differential equation is a description of a function that we don't know. Differential equations are important because this is a very important interface between mathematical analysis and real observations. So this is where we start making observations, not just based on the amount of things that we see, like the values of the function, but how the function is changing. And we start making statements that describe the function in relation to its derivatives. So this is really an important interface between reality and mathematical analysis. Let's take a look at an example of an observation that could be described with a differential equation. We're going to make an observation about a function in relation to its derivatives. This is going to lead to a differential equation, and then we can solve the differential equation. Now, this is going to be very contrived because this is a math class, and all the examples are very contrived to make sure they point directly at the thing that we're talking about. But we need an example to see how this goes. And we should start with something familiar. That's one of the things that I always try to do. Start with something we already know. If you've got a technique for finding the area of something, you should use that technique to do something like find the area of a circle to make sure the technique is going to work, because we already know the area of a circle. So let's start with the following observation. The rate of change of a function is proportional to the value of the function. The rate of change of the function is proportional to the value of the function. This is what we see that comes up in population growth. Maybe we observed that larger populations grow faster. And maybe we've reasoned that that makes sense because a larger population has more members to make more members. So it makes sense if your population is twice as large, it can grow twice as fast. Clearly, there's going to be some limits to this. Eventually, we'll run out of space. And actually, before we run out of space, we'll run out of resources. And actually, before we run out of resources, we'll run out of political will to distribute resources effectively. But that's all beside the point. We just want to look at this core observation. The rate of change of a function is proportional to the value of the function. We made a mathematical statement involving a function and its derivatives. Here I said the rate of change of a function, that's the derivative of the function. Let's say that the function is y, then the rate of change of the function is y prime. So we're saying y prime is proportional to y. If y is twice as large, then y prime will be twice as much, twice as large as well. That's proportional. Y is telling us the size of the function. Y prime is telling us how the function is growing. And we're saying that these things are proportional. If two quantities are proportional, that means one is a constant multiple of the other. So we can translate this statement, this observation, into the differential equation that says y prime is proportional to the function. Proportional means one quantity is a constant multiple of the other quantity. Proportions means one quantity is a constant multiple of the other quantity. Your gross pay is proportional to the number of hours that you work. In that case, the constant of proportionality will be your hourly wage. The distance that you can travel is proportional to the amount of time spent traveling. The constant of proportionality is the rate at which you are moving. So when we say the rate of change of the function is proportional to the value of the function, we're saying that y prime, that's the rate of change of y, is some constant times y, which is our function. If the value of y doubles, then the rate at which y will grow doubles. Questions? How's everybody okay? Too much for a Monday? Weird. These are our simplest differential equations. We can solve this differential equation by looking at it. but we're going to want to develop techniques. So we know what this function is already. Mainly, partially because I said population. This is how we can model a population up to a certain point. And we know that populations grow, will grow exponentially unless you limit the resources in some fashion. Or put another population too close to it. And then that population will be like, ah, fuck those guys. And then they'll start fighting. That's for human populations. So we already know what the solution is. So we know that the solution is something times e to the k times t. Because we're looking for a function whose derivative is just k times the function. And that's this exponential function. So we kind of already know the solution. Pick something that you already know. So if y is equal to ce to the kt, then y prime is c times ke to the kt, just using the chain rule. Ce to the kt is what we started with. The derivative is k times ce to the kt. Solve this by observation or because we know. I told you this is a population problem, and that's usually where we start meeting exponential functions. It makes sense from looking at what the equation is telling us. Y prime is a constant times y. We know what function has that property. It's the exponential function. The derivative of e to the kt is k times e to the kt, k times whatever we started with. That constant multiple c gets carried along because we know that the derivative of a constant times a function is that same constant times the derivative of the function, so it doesn't affect anything. If I had a separate term, like e to the kt plus something, then we would lose out. That would not work because the derivative of a constant term is 0. So that would not fit this description. But a constant multiple, that's fine. Right now, we're not sure where that constant multiple comes from. Mechanically. But we can see where it comes, why it doesn't affect things by multiplying by a constant. Question. Pick something that we can solve just by looking at it. Good place to start. This particular equation is what we would call a separable equation. So note that I didn't use some kind of technique to find this solution. It was just a guess, and then we can check. The important thing to note here is that the solution is a function. our solutions are going to look like y equals some function, not just y equals some constant. So let's look at a technique that works on a particular kind of equation called separable. A separable equation is a particular kind of equation for which we have a technique. It's a particular type of differential equation that we can actually apply a technique to. I'm going to replace my my y prime with dy dt. I'm going to switch to Leibniz notation. Once I write dy dt, I'm explicitly stating that the independent variable is t. So y is a function of t. In this setup, y is some function of t. We call this kind of equation separable because we can separate the variables. I have y's and I have t's. I'm going to put the y on the left with the dy, and I'm going to move the dt over to the other side. So I'm going to have a y side and a t side. So we're going to separate the variables. This includes the dy and the dt. So on the left, I'll have 1 over y times dy. And over on the right, I'll just have k times dt. I could shift the k over with the y. It's just a constant multiple. Traditionally, we leave it over there on the left. Sorry, on the right. So we separate the variables, and now we integrate both sides. So the next step is to integrate both sides. The integral of 1 over y is natural log absolute value of y. The integral of the constant is k times t plus c. Now we integrated both sides, and that introduces a constant integration on both sides. But they're arbitrary constants, so I'm going to gather both of the constants on the side with t. So that plus c is both constants of integration. The two constants are not necessarily the same, so I can't just say that they will cancel out. They are arbitrary constants. I had some natural log of y plus c1 on the left and kt plus c2 on the right. Let's move the c1 over to the c2 side. Now I have a relationship between y and t, so I could solve for y to figure out what the function is. If the natural log of y is kt plus c, then y is e to the kt plus c. That's just the relationship between logarithmic functions and exponential functions. Natural log of y equals kt plus c means that y is e to the kt plus c. If you need more technique, we make both sides powers of e. We write e to the natural log of y is equal to e to the kt plus c, and then e to the natural log of y is equal to y. This doesn't quite look the same as what we had before. I had a constant multiple, and here I have a constant term up in the numerator. So then we're going to do some property of logarithm shenanigans. So e to the kt plus c is e to the kt times e to the c. We multiply things at the same base, we add their exponents. And the same thing applies in reverse. Oops. So that's just the properties of exponents maneuver. Now my e to the c is an arbitrary constant. C is arbitrary, so e to the c is also arbitrary. So I'm just going to call it c. C is arbitrary, so e to the c is also arbitrary. It doesn't matter what we call it, it's just some constant. So rather than giving the complicated name of e to the c, I'll just call it c. Questions? That's everybody okay? Notice that this c came from a constant of integration. And that constants of integration are the things that we don't know about. We need extra information to find out the constant of integration. When we differentiate a function, the derivative of a constant is equal to 0. So it's like we lose a piece of information. So just like we need initial conditions to find the constant of integration, this arbitrary constant, we will need initial conditions to find the arbitrary constant. Let's take a look at an example. So here's a differential equation. Y prime equals 0.5 times y. This will lead to a general solution. The general solution is in the same place as the general antiderivative. There's a constant of integration. In this case, because we started with the separable equation, it really came from a constant of integration. If we have an additional piece of information, we can use the initial condition to figure out the constant. So if t is 0, y is 100. A differential equation gives you a general solution. A differential equation plus an initial condition gives you a particular solution. Just like the general antiderivative is a family of functions, the solution to a differential equation is a family of functions. We use this abbreviation for differential equations. I think the current way to say differential equations and shorten it, because we always shorten the name of our top classes, is to say diffie cubes. This is different than the group of people I was coming up with. We just said DEs. Or we would differentiate between our ODEs and our PDEs. But then no one says that anymore. I hear people talk about diffie cubes. So I'm just going to try to be like, oh, I'll just try to do that too. This is math terminology. So it's not like old people trying to use the parlance of young people, which is always cringy and embarrassing. You know what I mean? It's one of the reasons that we have to have desks with the chairs attached, or a chair with arms on it, because otherwise you might get some math professor who tries to be cool and will take out the chair and sit on it backwards and just try to rap with the students. Try to be one of the cool youth pastors, you know what I mean? And then looks ridiculous in the process because I'm a 50-year-old man. And regardless of what I think about current music and what's popular and youth culture, I should not attempt to participate in it unless I look ridiculous. You know what I mean? All right. There are so many things that The Simpsons absolutely nailed. They haven't done it in a long time because The Simpsons hasn't been a decent show in a long time. It's just a parody of itself that for some reason, is it still on? It needs to stop. It needs to stop have needed to stop a long time ago. It used to be spot on in its observations. And now it's just so wildly out of touch. It's just ridiculous. It's embarrassing. You can tell if you're wondering when this happened, find out when Futurama started. Because Futurama is one of the best shows on television, in television history. It makes keen observations and it knew when to quit. Obviously better show. And all the writers from The Simpsons that were worth a damn went over to Futurama. I realize it's being recorded and put on the internet, but no one watches my videos. It'll be fine. I'm completely safe. The Simpsons will not send a hit squad after me. But if you're a Simpsons writer and you're offended by what I just said, take a look at your writing. Go back and watch those first few seasons of The Simpsons and realize that you are missing something. Anyway, what are we talking about? The Simpsons absolutely nailed a few things. And that's one of them. I can remember distinctly. Some guy was trying to connect with the youths, and so he sat down backwards on the chair because it's shorthand for demonstrating an old person that's out of touch. The other one is the one where Bart nominates Mrs. Krabappel for some teacher award. And the selection committee is sitting there watching video submissions. And there's one teacher that's like, oh, I like to use humor to connect with my students. And it shows them doing impressions. Essentially, doing an impression of Robin Williams doing impressions in the classroom. And one of the observers says, Dead Poet Society has ruined a generation of teachers. And this is absolutely fucking true. Because too many non-teachers, young teachers, saw Dead Poet Society and said, I want to be that. And it was as ridiculous a request or a ridiculous a fantasy as watching Superman and saying, I want to be that. That's not how this works. Dead Poet Society, Robin Williams had a writer. And moreover, everybody in the classroom was part of the same script. That's why it worked. And so all these young teachers say, oh, I'm going to do that. And I'm going to be amazing. And when I walk out of the room at the end of the semester, students are going to stand on the desk and be like, oh, Captain, my captain. And that's not going to happen. That is a ridiculous thing to strive for. So 100% true, Dead Poet Society, ruined a generation. Hopefully, we're coming around and we're realizing that that's not the way it works. And we just try to be our authentic selves. Even though I admit that the role of Professor Leach is a role that I play, it's a character that I play, it still needs to run close to the real person so that there can be some authenticity. You know what I mean? What are we talking about? Oh, yes. So you take character traits that are authentic to you, like easily distracted and says takes way too long to say anything. Character traits that I share with my character of Professor. You know what I mean? You're like, well, shit, yeah, we know what you mean. It takes you forever just to say anything. So we are familiar with this. We've been in your class for 14 weeks. And we still wish you would just shut up sometimes. So. The differential equation defines a family of functions. And then we need some additional information, an initial condition to figure out a particular solution, a particular member of the family. So the solution to a differential equation is a family of functions, the initial condition. Chooses a particular member of the family. The differential equation is main characters in the movie The Godfather. Initial condition is the weak one. Then you know it's Fredo. The initial condition told you that the family of solutions was Corleone. The initial condition told you that it was Fredo, a particular member of the family. Any questions? Notice that in the CE, just thinking specifically of these exponential functions, that the 0.5 came from the differential equation. That was an essential part of the differential equation. The 100 came from the initial condition. Newton's law of heating and cooling is just a vertical shift of the exponential function that we had before. But a lot of us haven't encountered Newton's law, so let's talk about it now. Newton's law of heating and cooling says that the rate at which an object cools, talking about derivatives, because here the rate is proportional to the difference between the temperature of the object and the temperature of the surrounding medium. The rate at which an object heats or cools is proportional to the difference between the temperature of the object and the temperature of the surrounding medium. If you take a hot potato out of the oven and stick it on the counter, then the difference between the potato will be cooling slower than if you take the hot potato out of the oven and stick it in the freezer. Unless you keep your house exceptionally cold. But I have not seen Victor Freeze enrolled in my classes, so I'm not worried about it. Works the other way. If on a cold day, your cup of coffee will cool faster than on a hot day. But we're using the same setup. We're still going to get an exponential function. We're just going to not be heading exponentially towards 0 or infinity. We're going to be heading exponentially towards some finite limit. But the setup is very much the same. The rate at which an object heats or cools, this is the derivative. The temperature of the object is still the function. We're concerned with the difference between the temperature of the object and the temperature of the surrounding medium. So the surrounding medium is going to be a constant temperature. I usually use R because I'm going to eventually default calling this the room temperature. But it works even if we're not dealing with a room. Moreover, to simplify our lives, we're going to say that the temperature of the surrounding medium, the room temperature, will be constant. Otherwise, we just start actually being ourselves to death. Because if I bring a hot cup of coffee into the room, technically the room is actually a little bit warmer. Because the room is going to cool down the coffee, but the coffee is also going to warm up the room. But I mean, really, which one's going to do it? Furthermore, I'm putting the cup of coffee in this room, and the temperature is not constant throughout the entire room. For one thing, it's going to be warmer near the coffee, and it's going to be cooler over there by the wall. So we're simplifying our lives by saying the room is just going to be a constant temperature and not worry about the variability in the room and not worry about the cup of coffee affecting the temperature of the room. Because it's really not going to. Even if that coffee is stupidly hot, like 190 degrees Fahrenheit because America, it's not going to really warm up the whole room. But we have the same structure that we had before. We have a proportion. We're saying, and we're going to translate this statement into an equation. The rate at which an object heats or cools, that's y prime, is proportional. That means it's a constant multiple it's proportional to the difference between the temperature of the object and the temperature of the surrounding medium. We've taken our statement and translated it into math. Our statement involved rates of change, so our statement involved derivatives, so our equation is a differential equation. And we know that there are going to be two possibilities. If we have a constant room temperature, that's going to be our asymptote. We know our solution is going to look like some function. Either we're going to have some hot object cooling off to room temperature following an exponential function. Or we'll have a cold object coming up to room temperature. I want to mention how stupid English is because the object that we say heating up, but we also say cooling down. We should be saying heating down, and it's like -1 times heating. Heating. That means just cooling, right? But we say cooling and then down as well. So we can see what the solution is going to look like. We're going to have the constant in the middle. We'll have R plus CE to KT. I know that there's some part where the exponential part is below R. That just means C will be negative. So I don't bother with writing plus or minus. C is negative, means we're starting below room temperature. C positive means above room temperature. We can also see from this setup that over time, the temperature of the object should be approaching the room temperature. And so we can also see that K is going to be negative. We should also note that this equation is separable, so we can solve it using that technique. Here we solved it by knowing what's supposed to happen. Knowing that we're going to get an exponential function heading towards room temperature rather than 0. So we solve this by observation. Because as usual, the point of a math class is not to be able to do the math, but not to have to do the math. The whole point of doing all that math is so that you can avoid doing all that math. Questions? Comments? Snide remarks? All right, that's going to be it for today. I will see y'all on tomorrow. Everybody have a good day. Thanks for playing.